Well, folks, good evening and good afternoon. Thank you for staying on. This is our last session of the summit, so I'm really honored to be with you here today. We have a really hardy bunch left. Sorry, I will speak in English. I'm still working on my Hebrew, though. Could probably do a presentation in Russian, and I bet some of you can understand that. So my name is Denis Batalov, and I work as a solutions architect in the EMEA region, specializing on machine learning, big data analytics applications. Today, I'm going to talk to you or walk you through a specific use case. Now, the Titanic dataset, and some of you have seen the previous presentation from Guy, is actually exciting, and I'm really impressed with how well the model can predict things with that dataset. But today I'm going to take something specific, perhaps a little bit more practical, which is the problem of churn prediction, and try to explain how we can build a practical kind of machine learning model and application with this. So, churn prediction, or churn, customer churn, right? This is a very common issue, a common problem that different companies face, right? If you offer a service of some kind, then you may have customers leaving your service, abandoning you for some reason, right? And there could be many reasons for that, but you know, they may be leaving to your competitor, they may be just abandoning the service, and being able to know ahead of time that this customer is a likely candidate to leave is very valuable because A, you may not have to reacquire this customer or reacquire a different customer if you could retain them with some sort of perhaps loyalty inducement offerings, right? And that has a substantial implication to your kind of bottom line. Now, we're going to try to take machine learning and apply this to the churn prediction problem. And of course, machine learning, we have a lot of customers who obviously heard of machine learning. But one of the challenges that we're facing is that there's a lot of confusion and lack of clarity as to what exactly is machine learning and how you can apply it to specific problems. So a lot of my time is actually educating customers in the specific problem sets and how machine learning can be applied to your problems. And of course, you know, machine learning is a subdomain of artificial intelligence, which itself as a field is drawing from a lot of different other sciences like, well, computer science, of course, but also neuroscience, biology, operational research, and so on and so forth. But we're also now seeing that a lot of that scientific effort is now going into practical engineering applications, right? And so we need to marry the science and engineering here, and that's what we're seeing. So just a quick kind of high-level overview of some of the types of machine learning that you could be doing. For example, in robotics, and even within Amazon now, with Amazon Robotics as a subsidiary, is building these robots, also known as drives, that are driving the pallets. And you can think of some applications of machine learning there because, for instance, imagine that this drive has a wheel or some kind of thing that is malfunctioning at the moment, right? And well, of course, you could go ahead and repair it, but you could also, if it's a slight malfunction, you could try to learn how to work around this malfunction, right? And still have the robot, you know, move in a controlled way. And a similar thing you can imagine with kind of prime air drones, where maybe a gust of wind or some other distraction could affect the standard closed-loop kind of algorithm for the robot, and you could try to recover and make some adjustments and learn from this. And some of these things, you know, this picture I like because it explains of how some kind of learning like this could be done. It's through trial and error, also known as reinforcement learning, where a robot is experimenting with its environment and being reinforced, or, you know, in a carrot and stick approach, stumbling on rakes in this case, learning the hard way how to behave. Another kind of application could be image recognition. And in fact, when we launched the Amazon mobile application for shopping, I was working on that team. I was the first engineer on that team. And when we launched this product, we had this feature where you could snap a picture of a product or something, and we'll identify the product for you and send you a link to Amazon where you could buy this. Now, in the very first early version, this was 2008, we actually used something called Mechanical Turk. I don't know if you guys heard of Mechanical Turk. How many of you have heard of it? All right, great. So this was a fun artificial intelligence kind of a tool that allows you to kind of have humans work on these intelligence or human intelligent tasks. Of course, later on, we'll replace this with a true automated software. In fact, you may have heard of deep learning, which is now very popular, and a lot of kind of applications for image recognition is based on the deep learning approach, and Amazon actually open sourced a library called Destiny, which allows you to build deep learning applications. But what we're going to talk today about with the churn prediction is a supervised learning approach, which is a classical supervised learning. Imagine a kind of complicated system which may have human components, it may have automated like machinery components, and it's behaving in a certain way, and we'd like to be able to understand and predict and model this system, right? So typically what we do is we collect a bunch of inputs that go into the system, observe a bunch of outputs, and we amass a history of these, right? And we pass that history of observations into the machine learning model, or into the machine learning service, in this case, an Amazon machine learning service, to build a model out of this historic data of how the system behaves. And hopefully this model then can work on a new unseen input and reproduce an output or outcome that is similar to what a real system would have done. In this case, we could talk about numeric regression, we could talk about classification problems where this model is producing. And in fact, Amazon machine learning model can produce binary kind of classifications, as Guy just showed. You can have multi-class prediction problems that it works with, so predicting that the data point is one of the few classes, and a numeric regression. Now, in this case, tying it back to the churn prediction, we're going to build a binary classification, binary model that will tell us whether this customer is about to leave your service. And in this case, the service that we're going to use as an example is a telecom cell phone operator, right? Very common, very familiar use case to all of us. You know, people are constantly angry with their cell phone providers, and they're opting to leave for their competitor, and then discovering that they're also not that bad, not that good, and may want to come back, right? So the data set that I'm going to use here is something that has been published before. There's actually, this is included in a book. You could find it online as well. It's using, about 3,000 kind of data points, and each one of them contains 21 different attributes. So first of all, there's information about the customer, who is using the cell phone plan. So it's a US data set, so we're having a state, the area code, the actual phone number is there too, but we'll see later on that maybe it's actually a synthetic one. There's some Boolean attributes. Does this customer have an international plan enabled, a voicemail plan? Now, this data set has some age behind it. And then there's also customer behavior, right? How many voicemail messages on average do they have? How many minutes they use during the day, during the night, how many international calls they make, and so on and so forth. You can see the full list. And then there may be some interesting ones as well, like how long have they been with the company, the account length. And perhaps even more interesting, how many customer service calls have they made? Because this could actually be highly informative. I mean, that might be a guess of ours, right? If you've been calling customer service constantly, maybe you're not happy with what's going on, or you don't understand how the service works, and you may be, about to leave as a result. Of course, if you're just starting the service, it's possible that you're calling customer service to find out how things work, and that's normal and doesn't actually mean that you will churn. And ultimately, this data set has information about the target attribute, which is churn. Right? We want to learn this attribute. We want to be able to predict true or false, this customer is about to leave. And of course, we have 3,000 records of previously observed customers, and we know their attribute, whether they've churned or actually stayed with the service. So it's always important to know that with supervised learning, you have historical data. You have to have it to be able to build a model. Without it, it's not just, okay, give me some data and there's some kind of magic model that will be constructed. We're trying to model real, kind of previously observed situations. Now, this data set is pretty simple. This is literally an example of a CSV kind of file, and you see there's a state, area. Oh, actually, this is the account length, the number of days, 128, 107, and so on. The area code, phone number, and a bunch of other attributes, numeric attributes. And ultimately, the red one is the one that we want to predict. So 0 means the customer did not churn. The customer stayed with the service, and 1 means they left. And of course, in this case, this is just the beginning of the file, so to speak. Most customers actually do stay with the service. It's hopefully the minority that leave. Otherwise, you don't really have a great service at all. OK, so Guy has shown you, if you've stayed in the previous session, how a data source can be created, how machine learning is going to be built. So I will skip the steps of doing this. However, I think this is a good opportunity for us to switch to the console and perhaps observe. All right. OK, it adjusted the size. Observe something about the attributes. And this is actually very interesting because you could learn something about your data set in the process, even if the kind of data visualization and information provided here is fairly simple. But for instance, let's look at customer service calls. This is the attribute. We can look at kind of the distribution of the calls. And we see that quite a good number of customers actually don't make any customer service calls, so 0. But then, there are a number of customers, 1,000 out of the 3,000, approximately, made at least one service call, and then it kind of drops off. OK, so interesting information. Now, looking at the categorical attributes, and of course, let's look at binary, the actual target attribute, churn. We see that, like I said, the majority of customers did not churn, did not leave the service, and then this percentage has churned. Now, if we look at the percentage, it's about 14% of customers actually did leave the service. And this is an important number that will be useful for us to remember later on, so 14% or thereabouts. Looking at the categorical attributes, we see, for example, interestingly, area code. If we click on the histogram, well, there are really only 3 area codes here, 415, 510, and 408. But if we go back and look at the state, we see quite a few different states. In fact, carefully here, 51. Well, we have 50 states in US Dataset plus the District of Columbia, right? Washington, D.C., so that's 51. So how come? I mean, we have 51 states and only 3 area codes, right? And in fact, if you look at these area codes, they all belong to California, different, I think, San Jose, San Francisco. And so there's something fishy about the phone numbers themselves. And that's why I think there's a good chance that they were just generated synthetically because, I mean, there's this data privacy and whatnot. But this is an interesting bit that you could discover by kind of using this data source. OK, now, the next thing is building a model. So I've already pre-built the model previously. And what Guy was showing is a choice of a bunch of defaults. And that's true. You actually don't need to know how the algorithm works and what are the specific input parameters and whatnot. You could actually let the service choose the data transformations by default. So there's something called a recipe, right? And you can, this is one of the opportunities for you to actually control how your data is going to be passed to the model. What the recipe is doing, and I don't know if it's, this is a custom recipe that I've actually included here for this model. Maybe if we use, this might be a little bit more visible here. A recipe essentially tells you that you're going to perform certain operations to the input data before you pass it on to the model or to create the model. And the reason we want to encode this is because the very same transformations will need to happen when you try to predict stuff, right? Because your input data is going to go through this transformation at the time when we build the model and also at the time when you actually want to exercise the model. So we want to do it once. And what we're doing here is describing in several sessions, so there's outputs. Okay, these are the output attributes that are going to be used for building the model and that will inform the model. And we typically list individual attributes or groups of attributes here that go out. And all binary is the default built-in attribute that describes all the binary attributes. We have the same thing for like all numeric, all categorical. And then I can also group a bunch of attributes in the groups definition, where I say that all the numeric attributes, except the customer service calls, I will group them in numeric, and then I will apply the normalize function to these attributes. And we'll see in a moment what that means. But I'm leaving out the customer service calls because I'm thinking that this is a valuable bit of information. So I'm using some insights into the data set to affect how the model is constructed. I'm thinking that this attribute is going to be affecting the outcome quite a bit, and so I've decided to treat it differently. And again, this is an arbitrary decision that you, as kind of designer here, can input or can inform this process. You can kind of veer off from the default. Now, I think I've also skipped the phone number, thinking that maybe it's not useful. Mind you, the area code, we've just learned that the state and the area code, there's some suspicious situation going on, and perhaps we could have skipped those as well. And then that would have been really useful. I haven't tried that. You might imagine, if those were actually real phone numbers, you might imagine a situation where even the phone numbers could be useful. Sometimes you have no idea. There are some dependencies in data. For example, if I have a phone number that is hard to remember, maybe I'll be more likely to leave the service if for some reason I don't like my own phone number. I don't know. Who knows? But in this case, I've decided to not use that information. So back to normalize. What does normalization do? Well, it's trying to kind of transform the attribute into a kind of Gaussian, standard Gaussian distribution with mean around 0, right? So if these are different account length attributes, the number of days, then after applying the normalization, I'll get different set of numbers. So all the numeric attributes are kind of behaving the same way. They kind of have similar scale here, except the customer service call, which I left as is, right? So it's 0, 1, 2, 3, 4. And so if you've made 5 or more customer service calls, maybe that's going to sway the model a little bit stronger in the direction of churn. All right, so I went ahead and built the model. And you've seen this graph if you've been to the previous session. Here, we see the distribution of the data points and their scores from the testing data set. Remember, we had originally 3,000 data points. So 30% of those, about 1,000, were left aside to evaluate the model, and only about 2,000 were used to build the model. So this is the result of applying the evaluation to the 1,000 data points. And now I have a histogram, a distribution of scores for those data points. So if I'm closer to 0, right, that means I'm less likely to churn. If I'm closer to 1, that means I'm probably more likely to churn. And again, you're seeing a very practical kind of a graph, which is not clear, right? Like, what am I getting here? Is this a valuable result? Does this model give me something useful? So the gray line here and the kind of gray area under that line represents customers who do not churn, who do not leave your service. And while it's good that they kind of aggregate around 0, right? They stay closer to 0. We do have some of them that are actually all the way here. And more importantly, there's a lot of customers who do churn that also get a score that's close to 0. And so we're not making a great deal of differentiation here. Now, let me switch to the console real quick. OK. Try to use the evaluation. So note the area under curve 8.3. It's actually worse than the Titanic data set. But again, the area under curve, you have to be careful because it could also be misleading. For situations where the distribution of the a priori distribution of the classes is not even, right? In this case, we have many more non-churning customers than churning customers. This could, you may feel good about it, but it may actually be not so great. And now if we look at the graph, that same graph that I was showing you, if I move my threshold, I see that the errors change, and I can decide, OK, I'll go by the total number of errors, right? I want to minimize the number of errors. But as I move my threshold, I see that, at best I could get about 14%, right? This is about the lowest error rate that I can get. Now, is this good or bad? Remember, I mentioned the 14% at the beginning when we looked at the a priori distribution of our two classes. So even if we didn't use machine learning, if we just assume that no customers would leave us, we have such a great service, we'll just proceed as if nobody leaves us, we're going to be committing an error of 14%, right? We're going to be wrong 14% of the time. And here, with the machine learning model, it looks like it's also producing 14% error. So what have we achieved here? Is this really valuable? And it turns out that typically, you need to look a little bit deeper and start looking at the two different kinds of errors, the false negatives, the false positives. Remember, the false positive here means that a customer is predicted to leave but will actually not leave, right? And false negative is a customer is predicted to stay but will actually leave, possibly a worse kind of error to make, right? And we need to look at the costs of these errors, right? The relative costs. What is more important for me? And what kind of decision will I use once I employ this machine learning model? So for example, if I determine that a customer is leaving, right? I get the prediction of customer churn. I might spend some amount of money on gaining the loyalty of the customer, right? Maybe give them some sort of free upgrades or something like that. And that's a cost for me. And vice versa, if I am wrong and predict that the customer will not leave, but the customer will actually leave, right? I will have to spend quite a bit of money acquiring a new customer in place. Maybe it's marketing, maybe again, free hardware kind of that I have to give to this customer, and not to mention all the administrative costs of setting up a new account and so on and so forth, because I have to actually employ people in the field to service the customers, right? So if we look into this situation, let's switch to the slides. This is exactly what I was talking about, right? We have to look at the costs of errors, and if our model is saying true, the customer will leave, I will have to likely pay the customer retention cost, regardless of whether my model is correct or not. I will still try to gain the loyalty of that customer. So now we need to look at the practical numbers, right? And I could say that the 14.5, actually, 14.5% of a priori churn, right? If I just assume that nobody leaves my service, and the cost of reacquiring the customer is $500, which is actually not unreasonable. There are some publications, some companies say this is how much they spend. On average, you hear different distribution, 300, 400, 500, and so on. So it's not an insignificant amount of money. Then 14.5% of 500 means that for every customer of mine, on average, I will be paying $72 to keep the pool of customers the same, right? And now, if I take into account the cost, let's say, hypothetically, that to gain the loyalty of a customer, the retention cost is about $100. This is how much I'm willing to pay in terms of upgrades or some other loyalty benefits. Then I can say that with a particular position of a threshold in my graph and the particular relative percentage of false positive and false negative errors, right, the cost that I will get per customer is going to be different depending on where the threshold is. So instead of optimizing, and going back to this screen, instead of optimizing for the total errors, right, I need to find a position of this threshold that instead optimizes the weighted error, weighted by their costs. Now, how do you do that? You need to do additional work, because you will need to run the training data set, the testing data set, sorry, against the model that you've built, download the results, and then perform a numeric optimization of some kind, right? You could probably build it in Excel, or you could write a script. And that will minimize the cost and try to find the position of this threshold. So it's not something you could do visually here by simply dragging the threshold, but you will find the particular position. And in fact, I believe in this case, after running the algorithm, it's going to be, instead of somewhere here, which is 14%, you might actually find that it's even tighter around here. So we will be, our false positive rate is going to be higher, but that's OK. We're willing to spend more money in terms of loyalty and retention, even on customers that are not going to leave. It's not such a terrible thing, right? You might increase their loyalty even further. But we clearly want to minimize the false negative error when we don't discover customers who are about to churn. And so by performing this optimization, if we go back to the slide, this is what I've done here in this picture. Now, these are the resulting kind of percentages, 4.8 false negative, and then I combine true and false positives, which is showing 26.4%. And with a retention of $100, we get $50 per customer with the machine learning model, right? And so now you can actually compare the having machine learning model and not having a machine learning model in financial terms, which is kind of interesting, right? You can now convince yourself, yes, even if this is not a perfect system, and in practice, you never have a machine learning system that gives you perfect predictions, right? If that was the case, then your problem is probably too simple, and you don't need machine learning to begin with, right? But now you have something material to work with. And what's more interesting is that you can then try to decide, OK, maybe the churn cost is fixed for me, but the retention cost is something I can play with. So maybe $100 is too much. Maybe it's 50 that's sufficient for me to retain the customers. But And changing that will give you a different position of the threshold, different optimization that you can get as a result. So if you have, 100,000 customers, you could say, OK, my model now is saving me $2 million per year. That's great. Of course, in any kind of practical churn prediction, you have to look at many other things, right? Your model might be, your cost model might be more complicated. You may have different kind of customers, right, on different kinds of plans, and their churn rates might be different depending on the situation, right? But this now gives you a chance to make an informed decision and can apply machine learning with success. So folks, that's all I have for you today. Don't hesitate to provide the feedback, and toda.